So I think we are now ready to start. Once again, welcome to HSE University's online Master of Data Science degree programs industrial webinar. My name is Maria Tikhonova, and today we are going to speak about natural language processing, a very interesting and fastly developing fields of data science. And namely, the topic of today is pre-trained language models, transformers, and how they change NLP world and our everyday life. So a few words about myself. My name is Maria Tikhonova. I finished Moscow State University, the Faculty of Mechanics and Mathematics. And also I finished Yandex School of Data Analysis, where I studied data science and where I fell in love with NLP. Now I work in R&D NLP team in Sber devices. So the topic of my research there is basically the natural language processing and huge language models. By the way, we are going to speak about some of them today. And moreover, I teach in High School of Economics, namely I'm teaching this program. And also I teach disciplines connected with machine learning and data science. So what's our plan for today? Today we will briefly discuss what natural language processing is and where can we use and see NLP algos. Then we will speak about language modeling, the problematics. We will discuss what language model is, and then we will speak about how machines can read and understand the text and how they can generate the text talking with us. And finally, we will finish with transformers, the most powerful neural networks which exist in NLP today. So lots of interesting plans. Let's dive in. Basically, natural language processing is one of the most interesting and one of the most fastly developing spheres of data science. Natural language processing is about all the data science algorithms connected with text. Basically, machines, they cannot understand the language as it is. They know how to work with numbers. So for the computer to understand how to work with text, we need to create special algorithms for the machine to comprehend the text. Moreover, the text is a very unstructured data. And that's why for the computer, it's always challenging to work with such type of unstructured to semi-structured data like text. Moreover, users write with mistakes and so on and so forth. That's why we need to invent some other algorithms besides basic algorithms of machine learning, which can work with such type of data. Obviously, NLP has lots of different industry and business applications. Basically speaking, we see NLP apps everywhere nowadays. Chatbots, machine translation, search engines. I bet you all use Google basically every day. Every time you use the search engines such as Google, you basically use the NLP-driven app. Or every time you use machine translation, which is powered by powerful neural networks, you use the advances of NLP and the data science. So let us briefly discuss the application of natural language processing in our everyday life. First of all, as I have already mentioned, this is about search engines, Google, Yandex, and so on and so forth. Every time you write something in this search line, the neural net, it finds information for you working with texts. Then another widely used and well-known application is machine translation. I don't know. It's not a surprise to see a good machine translation nowadays. Google Translator, Yandex Translator, they work well and they're powered by the neural networks, by powerful language models. And today, machine translation is quite good. And for example, when I translate something from Russian into English, the result is pretty well. Then another vivid example of NLP is autocomplete and correction of typos. Like some engines like Google or like Grammarly, which help you to correct your typos. T9 driven by the neural networks and autocomplete, they have become very, very, very common in our everyday life. Most of us, they use T9 and text autocomplete when they write something in their messengers. We got used to it. So in order to use all these NLP-driven apps and in order to see all these advances of the applications of natural language processing, we need to teach the computer how to understand and to model the language. But before starting speaking about language modeling, let us discuss what does it mean to model something. How we can model the language. What do we mean under this phrase? What do we basically mean when we say we want to build a language model or we want to model the language? Well, speaking from the just the general user's point of view, when we say we want to model the language, we speak about the algorithm. We want to create an algorithm which can imitate the human's language, which can communicate with us, which can generate text and basically speak with us and solve the textual problems, like the textual tasks, like answering our questions, for example, or guessing the meaning of the words and so on and so forth. And how we can do this? First of all, we can imitate the work of our brain and we can create a powerful computer which can think and thus talk with us. But this way is quite difficult because we basically don't know what does it mean to model our brain and how we can imitate the process of thinking nowadays. Basically, what we can do, we can imitate the human's behavior and some humans and some things people do. We can model how people see, draw, how they hear, and how they write. So, how can we emulate the natural language? Basically, how can we make the machine to model the language? The machine is the algorithms which understand the number. So basically, when we want the machine to model the language, we need to explain what the language is on the language of mathematics, because mathematics and numbers is the language the machine, the algorithm understands, and the machine, it speaks in numbers. So the idea nowadays is to model the probabilities of the language. Basically speaking, we want to estimate the probability of different linguistic sequences. For example, the sequence of words or the sequence of characters. And basically speaking, when we say that we want to model the language, that means that we want to create an algorithm or to train a neural network, which for every sentence can estimate its probability. By the way, this may seem a little bit strange, why probability of the sentence, why definition like this. But if you will think about it, this definition is quite natural, and we all have our own language model inside our brain. For example, whenever we choose one option between the same similar sounding phrases, like the one you can see in the slide, Jennifer and Dan went to the desert, and Jennifer and Dan went to the desert. In one case, the word desert is written with 2 S's, and in the other case, the word dessert is written as 1 S. And trying to understand how to write this word correctly, we use our own inbuilt, if I could say, language model estimating the probability, and we will understand that probably they went to the dessert and not the dessert which we can eat. That's why we will choose the first option with double S, because from our common sense we will understand that most probably the highest probability is that they went to some place where it's very hot, no rain, and lots of sand, and not a huge cake from the candy shop. So basically, we all have our own inbuilt language models inside our brains, and we want a machine to mimic the language model we have. For automatic models, the probability of the sentence is the solution. We want to create a language model which can estimate the probabilities of the sentence. So we will choose the sentence with the sequence with the highest probability and create a model that makes that can estimate these probabilities. And between the phrases, the cat sat on the mat, and on the mat sat the cat, we will choose the first one. However, it's very difficult to know the real probability, to estimate the real probability of a sequence. But we can use a language model to approximate this probability. I see your question in the chat, and thanks for the corrections. I'm terribly sorry for the mistake about the dessert. About the Bayesian approach in general, I think that in general, like if we speak that Bayesian approach is the approach about probabilities, in this sense, yeah, we could say so. But speaking more formally, just the formal definition is that the language model, the model which can estimate the probability of a sequence. And speaking about the language, this sequence can be words, phrases, characters, and so on and so forth. And the goal is to create a model that can estimate these probabilities. And as a free bonus, the language models, they have the quality that they can generate sequences. How they can do this, you will ask? Very simple. If we can estimate the probability of every sequence, we can estimate the most probable continuation of the sequence. Given the beginning of the sentence, for all words in our vocabulary, we can estimate the probability of the continuation of this phrase with these words, with this word. And thus, we may choose one or the most probable continuation. Yeah, as simple as that. And that's why, basically, when we say we want to build a language model, basically, we want to build a language model which can generate the sentences. And generating the language, generating sentences is one of the most desired qualities of any language models nowadays. When we say that our language model is good, this means that it generates a very high quality text. And thanks to this property, it can solve many downstream natural language processing tasks. For example, using this generative property, it can answer questions, basically solve the classification problem, and so on and so forth. And a little bit later, just in a few minutes, we will discuss how modern language models, how they can solve different tasks using this property of probability estimation. All language models nowadays, they can be divided into two types: the count-based models or statistical language models. They are like the first language models which were invented, and they estimated the probabilities of sequences using some static measure. They counted the number of times the word or some phrase occurred in the text corpus. They performed matrix factorizations, and basically they estimated the probabilities, the desired probabilities, using different statistical methods. They worked pretty well. However, in recent years, language models based on powerful neural networks, they showed very good quality. And that's explainable because neural nets, they are powerful, like data science toolkit. And it's difficult to imagine modern NLP without neural language models. They're practically everywhere. Machine translation, once again. And the language models we are going to study today, namely the language models based on the transformer architecture, all of them are huge, powerful neural networks, basically. And we will see that nowadays, all state-of-the-art language models are neural-based. But before we start speaking about all these huge transformer models, let us discuss how the machine can understand the words, how it can understand the text in order to generate. Machine models, they see data differently from how we do. They understand numbers, but how to understand the text? For example, how to make the phrase "I love NLP," it's awesome, understandable for a machine. The idea to present words, to represent words as vectors, that is called word embeddings. So why word embeddings? Because the machine, it knows how to work with vectors. For the machine, the vector is very understandable format and is a very convenient format, but it doesn't know how to deal with words or text. That's why the natural idea arises to present words as vectors. So basically, when we have our NLP algorithm, we have the input text. I love NLP, it's awesome. Then we split basically the text into tokens. Maybe it will be words, sentences, or just characters. These tokens are the units we are going to work with. Then we present every token. For example, we decide to use words as tokens as a vector. And then finally, we can apply our neural network and use it in order to solve the desired task. So that is the basic pipeline of how we can solve the NLP task nowadays. So speaking about word vectors, how we can embed words as vectors, how we can present our words as vectors. The most simplistic approach is one-hot encoding. So basically what we can do, we can enumerate all the words in the vocabulary and then to one-hot encode them. That means that we will present each word as a vector with only one on the ith position if the word has index I in the vocabulary, and 0 on the rest. So basically we have a huge vectors. The size is about the size of the vocabulary, and the vocabulary is quite huge. You can imagine. And they have only one non-zero number in it. This approach has place. It's very simple. It's a very simple baseline, but it exists. However, it has some obvious disadvantages. These vectors are quite huge, are very huge, basically, and they are sparse. They have many zeros. So it's quite an inefficient use of memory. And moreover, these vectors are orthogonal. The scalar product of every two vectors is orthogonal. And that's why the scalar product doesn't make any sense. So probably we want to make our vectors a little bit shorter, but more meaningful. For example, we want the vector, we want the scalar product to convey some meaning about the closeness of the word in the our vocabulary. For example, we want the synonyms to have the close scalar product and the antonyms to stand far aside one from the other. So what is the meaning and how we can convey and how we can train our embedder to understand what words are close, what words are synonyms, and so on and so forth. And here comes the idea to define the meaning of the word from the word's context. For example, let us look at the example. We have the word Trollinger. Before preparing for this lecture, I didn't know what does it mean, but I can look at the context where we can use this word. Don't drive after Trollinger. In Italy, Trollinger is known by the names Werner and Xavier. A bottle of Trollinger was on the table. The Trollinger grape and the wine brand of the same name is grown in the German region of, sorry for mispronunciation, Württemberg. So we can understand the meaning of the words just looking at the context where the word is used. So basically, just looking at these examples and the context of the word Trollinger, we can understand that it is a sort of wine and it has nothing to do with trolls. And that is the main idea which lies behind the most more advanced word embedding algorithms. The idea is words which frequently appear in similar contexts, they have the similar meaning. They are similar and synonyms. And we need to put information about word context into word representation. In this case, these word representations will be meaningful and we may use them in more like common way. So our idea is that we will build a dense vector. I mean that it won't have so many coordinates at the vocabulary length. It will be about 100 or 300 dimensional vectors. And this vector will be chosen in such a way that words appearing in similar context will have similar, not exactly the same, but quite close vectors. And as I have already mentioned, we will call these word vectors word embeddings or word neural representation, because we will use neural networks in order to create this word representation. Speaking about word embeddings, one should mention word-to-vec, one of the first neural approaches which was state-of-the-art for many years. It was proposed by Thomas Mikolov in the year 2013, and the approach showed really very prominent state-of-the-art results. And still, even after the appearance of transformer models, nowadays it is often used as a baseline. So let us discuss the idea, the prominent idea behind word-to-vec. So the name word-to-vec, as you can guess, is conveys the idea to present words as vectors. The idea behind word-to-vec basically is very simple. We want to learn word vectors by training the neural net to predict the context. So how we can do this and how this is realized in the word-to-vec algorithm? We will take a huge text training corpus. And for each sentence, we will go over this text in a sliding window. At each step, we will have one focus word, and we will compute the probabilities of the context word. And we will adjust the vectors in such a way that the probability of the context will increase. So basically, we will try to predict the context words by looking at the current word. Or another variant of this architecture, each time we will look at the context of the word, of the current word under consideration, and we will try to guess the current word to adjust the probabilities of our language model to predict the current word. Returning to our example with the word Trollinger, we will look at the sentence, don't drive after, and we will try to predict the word Trollinger, and we will punish our language model if it will make a mistake in its prediction, and we will give it some reward. We will reward it somehow if it will guess the word Trollinger in the desired context. Then we will just move our sliding window and we'll try to predict the next word. For example, in the third example, first we will try to predict the article a, then we will try to predict the word bottle by looking at its surrounding tokens, like a of Trollinger. Then we would predict of, then Trollinger, and so on and so forth. So basically, that's why the model is trained. And the architecture is very simple. It's a 3-layer neural network with one hidden layer. So our just idea is to incorporate all the information in this hidden space, and then we predict either the context words or the word under consideration. And basically, this word vec, it has two model variants. The first variant is the most common and the most widely used variant because it showed better results is skip-gram model. The idea under the skip-gram model is to predict the context, the outside words, given the center word. Returning to our example with banking problems, we have the sentence, problems turning into banking crisis S. Here, the current word is banking, and we want to predict the context word in a sliding window of size 2, which are turning into and crisis S. And the second type of word vec is continuous back of word. Here, the idea is the one I discussed when we spoke about the word challenging. We want to predict the center word from the context words. Here, like turning into crisis S, and we need to predict the word banking. The idea, so you see, the idea is the same, but like these two types of word vec are like the transpositions, if I could say so, of one architecture. So they do the same, but in the inverse. So basically speaking, the first skip-gram configuration is more popular nowadays because it showed better results. However, speaking about some computational things, in order to compute this negative skip-gram, we need to compute some very hard probabilities. We need to compute softmax over the whole vocabulary. It's better and time consuming. And speaking about word vec and the skip-gram variants, you will get acquainted, you will definitely encounter the collocation negative sampling and negative samples. Basically, if we would just straightforwardly try to estimate the probabilities of the context of the word given the context, the formulas would be very, very, very huge. So the idea is not to solve the original problem, but to change the training objective and to solve the problem of binary classification. Basically, we would create the pairs of words and their contexts, and we would train the neural net to just guess from this pair whether it is a real pair or not, or whether it is a negative sample, the example which does not exist in the context, whether this context and the word really can appear together or not. So basically, we would try to solve the problem of binary classification, whether it is a real word and context or not. And it proved to be faster and less computationally expensive. However, the question arises, okay, we can create this positive sample just from our training corpus, but where can we find the negative samples? How we can create these pairs of words in their non-existing context? The idea is if we would sample randomly the negative examples based on the empirical distribution of words, then these examples would never appear in the vocabulary just because the number of possible pairs is too huge. That is the idea behind the negative sampling, which proved to be very prominent. And that's why most of word-to-vec architectures are skip-gram negative sampling architectures. And the good thing is that the obtained vectors, obtained word2vec, and their modification. Vectors are very, very, very meaningful. They show the semantic and syntactic relationships in the linear space, in the linear vector space. Basically, we encode each word into a vector. And a lucky property, we can just make normal vector operations, like we can sum up two vectors, we can subtract the vectors, and we will obtain something meaningful in terms of words. For example, this is a very, very, very well-known example from the original paper. King minus man plus woman equals the queen. Just performing the operation on the vector level, we will obtain something meaningful in terms of words. Another example is big minus small plus smallest equals biggest. So this is very good. These vectors are not that sparse. The number of dimensions in most word2vec vectors is about 300, for example. This is nothing compared with huge one-hot embeddings. And we can perform some vector operations with words. Basically, we can subtract and add words. Moreover, these vectors, they have these desired properties that incorporate that synonyms are embedded into closed vectors. 1 second. No, not 3-dimensional, 300-dimensional, 300. So they have 300 coordinates, but you can use 100 or 500. Just adding more dimensions, it makes the training process more computationally expensive, but still it can exist. And 3 dimensions here on the picture is just the projection into 3-dimensional space, because we humans, unfortunately, we couldn't imagine the 300-dimensional space. And mostly these, the normal word embeddings, they start from 100 dimensions. And here, this is just the illustration, as you can guess. So, algorithm we discussed before, they produce vectors for the word. They don't know how to deal with polysemy. They embed each word into one vector. And for example, in this example, you can see in the slide, the house stays on the river bank and the criminal robbed the bank. The word bank will be embedded into the same vector. However, in this case, the word bank is used in 2 different senses, but they have the same vector, and that is the problem. And we may use the context embeddings or language models to cope with this task, because language models, they can distinguish this case by modeling the probability of the language. And this brings us to the transfer learning and the most powerful language models which exist today nowadays, the transformer language models. The general idea behind the model language models is to transfer knowledge from one general source to other some task-specific sources. Before, for example, if we wanted to solve the classification problem, for example, we have the problem of spam filtering, we need to perform the binary classification, whether the letter is a spam letter or not. We will use these word embeddings as an input for the machine learning algorithm, like XGBoost or random forest. We would use the word embedding for the task-specific models. And now we will use the whole language models, and we will train it to solve the task we want. So basically, we train the original language models which know how to model the probability of the language to solve our task-specific task. And thus, we will create a fine-tuned or trained on this specific task model. We will create the fine-tuned language model for this particular task. And here, transformers is the solution. So basically, nowadays, most NLP application and most NLP algos, they use pre-trained plus fine-tuned paradigm. The idea is to train a language model on a very, very, very huge text corpus, like all Wikipedia, all the available source in the net. These are the gigabytes of text, basically, and we pre-train the language model to model the language. That is to estimate the probabilities of every sequence. Now we have a very, very huge and clever neural networks which knows how to model the probabilities and which can generate the text. It's a clever language model, speaking about the text in general. However, it knows nothing, unfortunately, about our particular task. And let us consider once again the task of filtering the spam. For every letter, we need to predict whether it is a spam letter or not. And then this model is called pre-trained, and pre-training is quite computationally expensive. It takes usually weeks or even months on several hundreds of GPUs nowadays. And when the language model is trained, the weights are saved. Now it's clever and hopefully open source. And then in order to teach it how to solve our particular task of spam filtering, we need to fine-tune it to teach this language model how to solve our particular task. For this, we need the training corpus suitable for our task. It's not that huge at the original pre-training corpus, but hopefully it will be quite large. And on this corpus, we will train our pre-trained language model. We will fine-tune it to solve our downstream specific task. And this is called the fine-tune pre-training plus fine-tuning paradigm, because first of all, we pre-train and we create a huge and clever language model. And then we fine-tune it for our downstream specific task. And here, for this type or for this paradigm, transformer architecture shown in the slide has shown a very prominent, results. Today, our lecture is quite introductory, and the transformer is one of the most difficult things to understand during the course of natural language processing, all the background mathematics. I won't go into the detail today, but the idea is that this architecture was proposed in the year 2017 and has proved to be state-of-the-art since then. The key idea of this architecture is the attention mechanism. The idea behind the attention mechanism is to mimic humans' attention in some way. We feed the sentence into these neural networks word by word. And when processing each word, using the attention mechanism, this neural net understands what context words are really important in order to understand this current word and in order to estimate its probability. And that's why the mechanism is called the attention mechanism. And thanks to it, the results are very good. And so today there exist lots and lots of models based on the modifications of this transformer mechanism. and the transformer architecture. The zoom of language models is different variants of transformer models are called the zoo of language modeling, is quite huge. And one of the most popular neural networks, which showed state-of-the-art results 2 years ago, and now it is widely and commonly used, is called BERT. So BERT is a transformer-based neural network from Google, and it was pre-trained using the mask language model on objective. It was originally pre-trained to predict the masked word in a sentence. So in the pre-training phase, it tried to predict the masked words in the training corpus. And moreover, in addition, it was trained to predict whether the next phrase is the proper continuation of the current phrase or not. So it was basically pre-trained to predict the masked words and basically trained to predict whether the word is a valid continuation. I see the question, what is the difference of RNN with the attention mechanism? Basically, the RNN incorporates all the information in one hidden vector. And that's why it's prone to forgetting and so on and so forth. And the attention mechanism, the self-attention, for each current token, it estimates only several most important words. Not the attention mechanism allows not to consider all the previous words, but to concentrate on the most important. And if you want to know the details and the mathematics, because without the mathematics, these are only words, just come to our Master of Data Science program, and there we will study the mathematics. And it's quite difficult, but if you understand this, it will be very, very cool. And I hope to see you on our NLP course on Master of Data Science program. This is really going to be interesting. So returning to BERT, our pretty BERT is one of the most popular language models which exist nowadays. And it has its brothers and sisters like Elmo, Ernie, Robert. All of them are transformer-based and they show prominent results. Good news for new data scientists. There exist many of open source pre-trained model, because don't try to repeat this at home in your Google Colab. Pre-training a huge language model which shows good quality is very computationally expensive and requires lots of the GPU. That's why it's expensive in a real way. However, there exists a very good library, for example, Hugging Face library, which provides a very convenient toolkit for working with the pre-trained language models, and fine-tuning BERT for your specific task is very simple and is very convenient and is not that difficult, and it's quite fast, by the way. So you can fine-tune BERT for your own downstream task just in half an hour or in several hours, and that's it. You have your own fine-tuned language model which is able to solve your own the task you need. That's really cool. And so this thing is really, really cool. And this thing, how will I know which BERT model is the ideal for me? And this question, I see your question in the chat, how will I know which BERT model is the ideal for me? This brings me to the next slide. How can we measure whether our model is good or not? And just answering your question, how can we evaluate the language model? How we can evaluate that our model is really good and is really suitable for our task? In order to compare different language models, data scientists create benchmarks. A benchmark basically is a set of tasks for the language model. There exist several well-known benchmarks and the corresponding leaderboards on which the data scientists, they compare their language model. One of the most popular language, one of the pioneers in this field was GLUE, and one of the most popular English benchmarks is the SuperGLUE. For example, SuperGLUE, it contains 10 natural language processing tasks about the next sentence prediction, the question answering tasks with yes/no questions, the task on resolving word disambiguation, and it has a public leaderboard. And so most language models can be found on this leaderboard because it's very prestigious if your models show good results on this benchmark. And that's why, for example, if you want to choose an ideal language model which is able to solve the question answering task, you will go to this leaderboard, see the results. It's publicly available. Just Google the word SuperGLUE, and you may just look at the scores the language models show on the book-you task. The book-you task is the task for the yes/no question, the question answering task, and choose the model which is the best. That's why it's a very good question. We need to evaluate the models. We need to pair them somehow. And the most common approach for comparing language models is the benchmark. So, to sum up, what we have learned today, NLP-driven apps surround us today. These days, our modern life is practically unimaginable without the fruitful, prominent language models. The core idea is the word embeddings, the embeddings of sentences, and so on and so forth. And we can convert any text sequence into embeddings. And moreover, we can model the natural language, we can imitate and generate it. And language models allow us to solve a huge variety of NLP tasks. And most prominent language models nowadays, they are neural-based. They are huge and powerful neural networks which can basically model the language. And one of the most, the best architecture proposed today is the transformer architectures. And they exist lots and lots of different variants of transformers nowadays, of transformer neural networks, which are very powerful and they rule. So, if you want to know more about natural language processing, if you want to learn how to create your own question answering system, which can answer the ultimate question of life, universe, and everything, I will be happy if you will study NLP and choose data science as your career and come to our Master of Data Science program in High School of Economics. We will work, we will study, we will teach NLP here, and we will tell you how to fine-tune BERT for the huge variety of NLP tasks. It's really very interesting. So I'm actually a data science master student and HSE. So that's great. I couldn't see Srin Jason. Oh, that's great. Probably you already have the NLP course, but if so, then you will learn how to create your own transformer architectures, and you will study all the background mathematics very, very, very soon. Hope that you will like it. It's really interesting. Is it possible to contact you to discuss some interesting points and ideas? Yes, it's interesting. Yeah, you can contact me via the email. I will write my email in the chat, I think. And speaking about the details of the particular program, just ask them in the question answering session, and my colleague will will consult you about the details of the program itself. So do you have any other questions? I will be happy to answer them. You may just type them in the chat or just ask them in the special section. So in this case, I was glad to see you today on my webinar, and I hope to see you in High School of Economics and come to our other open lectures, other webinars. It's very, very interesting journey of data science. Bye. Have a good evening. I see that you ask about NLP course on data science on Coursera. There exists a very good NLP course from High School of Economics as well. You can just Google NLP High School of Economics and you will definitely find it. So bye. Have a good evening.